Hey, what's up everyone? Welcome to the start of our fourth unit, which is going to be thermodynamics. Today we're going to go over the first law of thermodynamics, and we're also going to go over heat. So let's just get into it. Well, thermodynamics is going to split the universe into two sections. The first section is the system, and the second thing is the surroundings. So if you're looking at a system, that's just going to be products and reactants. That's going to be a set of products or reactants, or just a single product or reactant. So if you took like something like this water bottle, that could be a system. Our entire planet could be a system. Your house could be a system. Really, it's like anything can be a system, but surroundings is literally anything else in the universe. And so, um, when you're thinking, sometimes when you think about a system, you only think like the surroundings is like the immediate surrounding area and the immediate surrounding factors. But no, surroundings is everything in the universe. And the reason we sometimes don't think of it that way is because, like a distant galaxy all the way at the edge of the universe is not going to have much of an impact on the system that is, I don't know, your coffee or whatever. So surroundings is important to know that it's anything else, literally anything. This allows us to get into the first law of thermodynamics, which tells us that the energy of the universe is constant. And so if that means if a system were to gain energy, well, in order for the energy of the universe to be constant, then that means the surroundings had to have lost that exact amount of heat or energy rather. And so if a system gains, the surrounding loses, and if a system loses, the surroundings gain. And the amount, the absolute value of the amount that they lose or gain is going to be the same. And so really what we have is a transfer of energy. And though that transfer of energy can come in two forms. First of all is work. Work is just like an application of force over a distance. You've definitely done force. You like intuitively you know what work is. It's like kind of just pushing something, and so that's not as interesting. What is more interesting is heat. And heat has major applications in thermodynamics, so I want to get a bit more into depth about it. So heat is energy transfer between systems due to a temperature difference between them. And colloquially, we use heat and temperature almost interchangeably, but I want you to know that in chemistry there is a distinction. Temperature is based on the random motion of particles. So if you have a system where where the particles are moving really fast, we say that it has a high temperature. But in order for heat to be there, there needs to be an energy transfer. So temperature and heat are two very different things. Despite this, they can be connected. And the way you connect them is using this formula, which is Q, which represents heat, equals mass times the specific heat capacity times the change in temperature. Or Q equals mc delta T, and sometimes it's just known as MCAT. Now you might notice a new thing there, and that would be specific heat capacity, which is that little C value. So what is specific heat capacity? Well, let's start with what heat capacity is. Heat capacity is the amount of energy required to raise the temperature of a substance 1 degree Celsius. So you could have a sample that is, I don't know, like zero point 0.1 grams, or you could have a sample that's 4 tons or something. And so in order to kind of narrow down how much of a substance that we are raising the temperature of, we say that specific heat, hold up, let me just erase this. We say that specific heat capacity is the amount of energy required to raise the temperature of 1 gram of a substance 1 degree Celsius. In the case of water, it's going to take 4.18 joules of energy to raise the temperature of 1 gram of liquid water 1 degree Celsius. And you can kind of see why mc delta T works. Because if you know that it takes a certain amount of energy to raise the temperature of a substance 1 degree Celsius, well then all you have to do is multiply that values times the mass and the change in temperature. So if you know that it takes 4.18 joules to increase 1 gram 1 degree Celsius, in order to find how much it takes to increase 10 grams by 10 degrees Celsius, that would be a times 10 here and a times 10 here. So really it would just be the C value times 100. Now all this heat value would have to be determined experimentally. And so how would you do that? Well, you'd use an apparatus known as a calorimeter. And on the left here, we have a specific type of calorimeter called a coffee cup calorimeter. And it's basically you put like a coffee cup, you take a styrofoam cup. And the reason you use styrofoam cups is because it's really good at insulating heat. So all the heat transfer that occurs is not going to be lost to the surroundings. Instead, it's going to be contained in that system. And so when you add something to like a liquid or something like a reaction occurs, well, this thermometer is going to change its value. And whatever that value changes by is going to be your value for delta T. And you're going to know your specific heat capacity, and the M you're going to just know from the setup of your experiment. So if you were to use all that information, you could calculate the heat transfer that occurs in a system using this equation, Q equals MCAP. Let's do a bit of practice with it. A sample of 54 grams of methanol is heated from 25 degrees Celsius to 35 degrees Celsius. How much heat is required? The specific heat capacity of methanol is 2.48 joules per grams per Kelvin. That's one of the important things about like these types of problems is that you're usually given the specific heat capacity of the substance that you're working with. However, despite the fact that you're most likely going to be given them, I would also just know that the specific heat capacity of water is 4.18 because that just comes up a lot. So let's do this problem. We know that Q equals mc delta T. We're trying to figure out Q. We know our mass is 54 grams, and so your mass should be in grams. Your C is going to be your specific heat capacity, which is 2.48, as the problem tells us. And our change in temperature is final minus initial. So final is 35 and initial is 25. So if you were to multiply all these things together, you would get 1339.2 joules. And that's approximately 1340 joules. And then it would be in the proper a unit, which for heat, when you're calculating just Q, it's going to be in joules. And so that's going to be answer choice C, and we are correct. Let's move on to the next one. What is the final temperature when 20 grams of water at 80 degrees Celsius is mixed with 30 grams water at 20 degrees Celsius in an insulated container? Now be careful here. This isn't your straightforward heat question, because really what is going on is a transfer of heat. You have two systems, let's say water 1 and water 2. And so the properties of water 1 is that it's going to be 20 grams, and it's going to start off at 80 degrees Celsius. And then on the other hand, water 2 is going to be 30 grams and start off at 20 degrees Celsius. Now intuitively, since water 1 is at a higher temperature, water 1 is going to give off energy, and water 2 is going to absorb it until they reach a thermal equilibrium. And so that means water 1 is going to lose energy, but water 2 is going to gain energy. But from the first law of thermodynamics, that transfer needs to be equal. So whatever our Q value is, let's say the Q here is going to be X. The Q value for water 2 is going to be minus X. Think about why that makes sense, right? Water 1 is going to lose it, and water 1 gains it. So although they're going to have different signs, one is losing, one is gaining, the amount that they lose or gain is going to be the same. And so we can use that property to set up some equations. First of all, water 1, let's calculate the MCAP for that. mc delta T, we know that the mass is 20 grams. We know the specific heat capacity is 2.184, and the change in temperature, well, we don't know the final, so we can just leave the final as F, and then we know the initial is 80. And so that's for water 1. For water 2, that's going to be Q equals mc delta T, and that's going to be 30 grams times the same specific heat capacity since they're the same substance, and then the same thing, F minus 20 degrees Celsius. Now, using this property, we can set these almost equal to each other. So 20 times 2.184 times F minus 80 is going to equal negative of this value. And I don't want to write it here. So I'm just going to put it in here. And you just basically have to solve for F. And once you solve for F, you're going to get that F is 44. And that is answer choice B. And we are correct. So again, you have to understand that a transfer of heat occurs. And the transfer of the amount of heat, the magnitude of heat is going to be the same for each. So you can set up those two equations and set them equal to each other, just negate one of them and just solve for the final temperature. Now, there's another similar question. This is the last question that we're going to go over for this little section. To 100 grams water at 25 degrees Celsius in a well-insulated container is added a block of aluminum at 100 degrees Celsius. The temperature of the water once the system reaches thermal equilibrium is 28 degrees Celsius. What is the mass of the aluminum block? And then tells us the specific heat capacity of aluminum. So again, in this one, we have two systems. We have water, and then we have aluminum. The water is at 100 grams, and it starts off at 25 degrees Celsius, and it goes to 28 degrees Celsius. And on the other hand, the aluminum is, well, we don't know the mass, so let's just leave it as X. And we know that it goes from 100 degrees Celsius to 28 degrees Celsius. So again, the Q value for here is going to be X, and the Q value for this is going to be minus X. Using all this information, we can set up two equations, or we can set up an equation again. So for water, we know Q equals mc delta T. M is going to be 100. The specific heat capacity of water is going to be 4.18, and then the change in temperature is going to be 28 minus 25, which is just 3. And so that's going to come out to about 1254. And then if we look at aluminum, Q equals mc delta T. And so the mass here is going to be X. We don't know. We're trying to solve for mass. The specific heat capacity we're told is 0.9. And the change in temperature is going to be final minus initial. So 28 minus 100. And so if we were to simplify this, we would get minus 64.8x. And so now all we have to do is set these equal to, like, negate one of them. Let's just negate the one on the right-hand side. And at this point, we would just have to solve for x. And so we could just do that by dividing 1254 divided by 64.8. And that gets us about 19.4 grams. And that is answer choice C. And we are correct. So it was very similar to the first problem, except in this case, we had different specific heat capacities. In this problem, in the previous problem, the specific heat capacity were the same since we had two waters. They're going to be the same substance, but in this case, we had a water and aluminum, and therefore their specific heat capacities are going to be different. Now, as it turns out, you can mathematically represent the first law of thermodynamics using this equation, where the change in internal energy is going to be Q minus W. Q is the heat and W is the work. So when Q is positive, then that means heat has entered the system. But when W is positive, then that means the system has done work. So if you get energy, but you have to lose energy, you kind of have to subtract the energy that you lose. And that is exactly what this equation does. And you can kind of see like some calculations with it. You don't really need to know how to do calculations with this, because I guess these numbers are like these numbers are very hard to actually determine. But it's good to know that the equation for the first law of thermodynamics is the change in internal energy equals Q minus W. There's one more thing I want to go over, and that's the difference between endothermic and exothermic. In endothermic reaction, these are going to be reactions where energy flows, there should be into the system. And in exothermic reactions, these are going to be reactions in which energy flows out of the system. So if you had like a chemical equation, and this one's wrong too, that should be NaCl. If you have a chemical equation and you're told that it's an endothermic reaction, then you know that the bonds in the reactants are stronger than the bonds in the products. On the other hand, if you have an exothermic reaction, the bonds in the products are stronger than the bonds in the reactants. However, in both reactions, the energy lost or gained by the system must be gained or lost by the surroundings. So let's say you have like a cup of water, and in that water, an exothermic reaction occurs. And so as a result, energy is given off into the surroundings, which in this case would be the water. Well, if it's an exothermic reaction, then the temperature of the water would increase. But on the other hand, if if the reaction that occurred was endothermic, then that means energy had to flow into the system. And where did it get that energy from? Well, of course, it's going to be the surroundings. So that means that the temperature of the water would increase if an endothermic reaction were to occur there. That's all I have for this lesson. I hope you learned something, and I hope to see you in the next lesson, which I think, yeah, it's going to be on entropy. Thank you for watching.